So let's do a practice problem to see just how we would use our new understanding of the mole. What we learned is that the mole gives us two very specific conversion factors that we can use to convert between various quantities that we'll need to use in chemistry. The first conversion factor was that Avogadro's number, or 1 mole, equals 6.022 times 10 to the 23. And the way we'll be using it mostly for the time being is with units of atoms. And the second conversion factor was that 1 mole of an element will equal the atomic mass in grams. Of the element. So for this one, we need our periodic table. So there I've inserted in my periodic table that I can blow up and use when needed. So when doing any of these problems, we need to have those conversion factors memorized. Of course, you can't memorize all the numbers on the periodic table, but what I mean is you need to memorize that 1 mole of an element equals the atomic mass of that element in grams. But you do need to memorize the number 6.022 times 10 to the 23rd. You need to understand the concept so that when you approach these problems, you can use these conversion factors appropriately. So let's do our problem. What number of Fe, that's iron, atoms, and what amount in moles of iron atoms are in 500 grams of iron? So we've got more than one problem here. So let's do the first part. I'll highlight the part we're going to do first. We'll do what number of iron atoms are in 500 grams of iron. In any dimensional analysis problem, we always ask where we're converting. Whoops, I'm in my highlighter. Let me get my pen. Always ask where we're going from. I should say number 1 here. We're going from and what we're converting to. And since we're wanting to know what number of iron atoms, we're going to atoms. And we want to know from grams. So, to go from grams to atoms. Now what's interesting about this problem is if we look at it very carefully, when we try to approach it in 2 steps, what we're going to find out something here is that there's an easier way to do this than doing it the way that I've set up. So watch. When we do our from to to, we ask ourselves, do I have a conversion factor that gets me from grams of iron to atoms of iron? Well, let's look at our conversion factors. Where's grams? Okay, grams. Well, grams goes to moles. So I don't have a conversion factor that gets me straight from grams to atoms. I would first have to go from grams to moles, and then from moles to atoms. So we could do this in a two-step conversion problem. So we could answer this. But if we look here, our problem is asking us two questions. What number of iron atoms and what amount of moles of iron are in 500 grams? So really, it makes sense to do this in two steps. And to actually do this problem first. And you'll see why. So we're going to still convert from grams, but we're going to convert to moles first. So let's set up our problem. If we're converting from grams, we have our number there, 500.0 grams. Now, one thing that we want to get used to and we want to start doing right away is to always write out every single unit of measurement. It's going to become very important in the future. I promise you. You will thank me later. So 500 grams of iron. And we always multiply it by a conversion factor. We know in dimensional analysis that if we have units here, those same units must go down here. Grams of iron. Now, since I did have both of my units here, grams and iron, it makes this easier to see what conversion factor we're going to use. Where do I find grams of iron? I find it on the periodic table. So I know that this is the conversion factor I'm using. The atomic mass in grams. So I need to get the number that goes here from my periodic table. So let's blow that up. Let's find iron. Iron is right smack dab in the middle. The number we need is 55.847. And that is for every 1 mole of the element. If you remember back to our standards of measurement lesson, the abbreviation for mole is MOL. So you can leave off the E. It's a little less work. Alright, so that gets us to where we want to go, doesn't it? It gets us from grams of iron to moles of iron. And now we see why I chose to do this problem first. So we're going to divide 5 with 3 zeros by 55.847. get 0.9530712. Very long number for my calculator. But since we're doing this in 2 steps, we want to write out all our digits for the most accurate answer possible. And that will be moles of iron. Right? How many sig figs should my answer have? Well, I have 4 sig figs here, 5 here, so I'm going to go with 4. 1, 2, 3, 4, and my number would stay the same. So my answer, my final answer for part 1, if I write it in an expanded notation, is 0.08953 moles of iron. So that's how we do the problem. It's like any other dimensional analysis problem. The only thing that we've added on here are our 2 new conversion factors that we can now utilize, and we just have to memorize and recognize where to go to get what we need. Whoops, I need to erase that. So part 2 we can do now. Part 2 was initially going from grams to atoms, wasn't it? But we've already done the work of going from grams to moles, so really we're going from moles to atoms. So what we can use is we can use this number here I'm going to do this. This is the nice thing about technology. Multiply it by our conversion factor. We know that moles of iron is what must be in the denominator. I know what I'm going to atoms of iron. I'll look to my conversion factors, and we know that that's Avogadro's number. So atoms goes on top, moles goes on the bottom. It's 1 mole equals Avogadro's number. 6.022 times 10 to the 23rd. We multiply our number here by 6.022. I get and I'm going to write this to only a few digits. Nope, I didn't cancel out my units. There we go. We get 0.53915 when 6 times 10 to the 23rd. since I'm so close to it being in proper scientific notation, I'm going to make it that way. Go to the right, reduce, bring that down to 22, and then I'm also going to put this in the proper number of significant digits. So I got 1, 2, 3, 4 sig figs there, and then 4 there, so 1, 2, 3, 4. We're going to do there. We're looking to a 5. We need to stop and think. And we look to 5s. We have non-zeros after, so we are going to round up. So our final answer will be 5.392 times 10 to the 22 atoms of iron. So here we've done two types of mole conversion problems. We did an example of where we would convert from grams to moles, and an example where we would go from moles to atoms. Other examples would be where we could have done this all in one step, going straight from grams all the way to atoms. We would have just put this conversion factor right next door to this one. Now we wouldn't have seen this answer because we would have done it all in one step. And since the problem asked for both answers, is why we divided it into 2 steps. So you can do a gram straight to atoms problem, and you can go the other way around too. The problem may give you atoms and want you to solve for grams. So let's go and practice some other types of problems we might see. So here in our next problem, you see I've taken away our conversion factors because we need to try to memorize them. Our first problem here wants us to calculate the mass of 500 dot atoms of iron. So we want to go from atoms to grams. Now, let's think about our conversions. If we have atoms, what is the conversion factor that involves atoms? Well, that would be Avogadro's number, right? And we know that there are 6.022 times 10 to the 23rd atoms, in this case of iron, that are equal to 1 mole of iron. Well, does that get us to grams? It certainly does not. So now we have to ask ourselves, is there a way to get between moles and grams? Well, sure there is. So this is a 2-step conversion. We can go by saying 1 mole of iron is equal to, use our periodic table, forget what the number was, 55.847 grams. Because that's the molar mass of iron. Now we have our 2 conversion factors. We can set up our problem in dimensional analysis. We know that we're starting with atoms. Or, I'm sorry, we're starting with atoms. 500 of those atoms. 500 dot. Remember, the dot matters for sig figs of iron. If that is what is our unit, that must go on the bottom. We look at our conversion factors, find where we have atoms of iron, write the number there. 6.022 times 10 to the 23rd goes here. That's going to equal 1 mole of iron. That goes on top, that means. We're not to grams yet, so now we go to our next conversion factor. We know moles of iron is on top, which means moles of iron must go on bottom. That's associated with a 1. Grams of iron is where we want to go. 55.847 must go on top. Make sure you've done this right and our units cancel. Atoms of iron, atoms of iron, moles of iron, moles of iron. We've set it up correctly. Now we just do our math. So I'm going to multiply 500 dot times 55.847. Then I'm going to divide that by 6.022. And that's a nice big number that I can't read very well. It's 4636.91. And that's going to be times 10 to the negative 23, since that's in the denominator. And that would be grams of iron, not fluorine. Now, we need to do sig figs, right? We got 3 sig figs here, 4 here, and 5 here, so it's going to be 3 sig figs. Three to the 6th, that's going to round up. So it's 4640.91 times 10 to the negative 23. Let's put that in proper scientific notation. 1, 2, 3 to the left. Make that larger. So it's going to actually go to 0. Oops, no, that should be to the 23. That's negative 20 grams of iron. There's our final answer. So we can do multi-step conversions because we couldn't go straight between atoms and grams. We had to first go to moles. The mole is our bridge. Let's look at our last problem. Diamond is a natural form of pure carbon. What number of atoms, so we're solving for atoms, of carbon are in 1 carat diamond if 1 carat equals 2 grams? This is interesting. We've got a, looks like they threw us a conversion factor in here. So, what are we working with? We want to go from, it looks like carats. And then we want to get to, what does it say? Atoms. Well, they've given us a conversion for carats to grams. So we know that 1.00 carats is equal to 0.200 grams of carbon. So we got to grams. Now I got to get between grams and atoms. So this is essentially what we did up here, but backwards, right? So we know we first need to get to moles, and then we can get to atoms, right? So grams to moles. So it looks like we need to go from grams of carbon to moles of carbon. Well, where do we go for that? Well, the only place we're going to find grams of carbon is on the periodic table, right? Zoom in here for carbon. Carbon is 12.0111. Oh dear. What did I do? There we go. And now, all that's left is to get to atoms. We know that a mole of carbon equals 6.022 times 10 to the 23rd atoms of carbon. Well, this is definitely a multi-step conversion, isn't it? So where do we start? We start with our carats, which is 1 carat. Now, let me just stop here. Let's use a little bit of street smarts. We know the conversion is 1 carat equals 0.200 grams, right? And we're starting with 1 carat. Well, can't we just skip this first step? Yes, is the answer. We can start with 0.200 grams of carbon, because that conversion's already been done. So essentially we're starting with 0.200 grams. Sometimes a little bit of street smarts can help us. We can just turn this into a 2-step conversion. So grams of carbon goes on the bottom. Well, where's our grams of carbon? It's here, but that was for that conversion. It's also here because we want to get to moles. So 12.0111 goes on the bottom. And 1 mole goes on top. One mole is, or moles of carbon needs to go on the bottom here. And atoms is what we want to get to. And that's 6.022 times 10 to the 23rd on top. Cancel. Make sure we set this up right. Indeed we have. I just forgot my 1 on the bottom. And we do our math. So, what's our math? Well, let's go across the top first. 0.2 times 6.022. And then we divide, that's 1.2044, which we will divide by 12.0111. And I don't have much room here, so I'm going to move that answer down here, and I get 0.10027. Can't forget about our times 10 to the 23rd. Atoms of carbon. Now let's not forget about sig figs. Our smallest sig figs are 3. 0 is going to stay the same. So you have, and let's move our decimal over. Reduce it to 22nd. We have 1.00 times 10 to the 22 atoms of carbon in a 1 carat diamond. And there you have it. And that's the power of the mole.